started? All right. So I'll just make a couple quick remarks on the quiz. So this was definitely a bit harder than usual compared to the past two quizzes, but the reason why I made this quiz a bit tougher than the last two was sort of to give you an idea of how to, what kinds of difficult problems you might encounter on the exam. Because, for instance, this first problem, this integral, I pulled this straight from an old exam. So that's why I put this on this quiz. So that way you guys kind of know what kinds of things you should expect for the exam. So just heads up there. But other than that, I sent the statistics about quiz 3. I sent some common mistakes. So you guys can refer to that email I sent 2 days ago. So other than that, let's go ahead and get started then. So any questions on this? Any questions on the homework, anything? All right. I assume that the by parts problem stuff went well last night. Okay. I'll take the lack of known to mean yes, and we will move on from there. So we still have the first exam next Monday. The location is still to be determined, but that will hopefully be rectified either Sunday night or Monday morning. So yeah, let's go ahead and get started then. Okay, that was good. Let's get started. So, a differential equation is the new topic we're going to be discussing today. So that is an equation relating a function to one or more of its derivatives. Okay. So to give you some examples of what I mean by this, we have dy over dx equals 8 times x. Y prime is equal to t times cosine of y. Y prime is x to the 4th y plus xy squared. And the last one is dy dt is equal to sine of t times y plus t cubed. Okay? So these are all just basic examples of differential equations. For our purposes of this class, we're only going to focus on differential equations with just y prime. We're not going to have y double prime in this class. So, okay, so that's that. And then a differential equation is known to be separable if it has the form y prime equals f of x times g of y, or y prime equals f of t times g of y, depending on what the input variable is. Okay? So to give you some examples of what I mean by this, let's take a look at the examples above to see what's going on. So to give you an example of what I mean by this, so with this problem here, this differential equation, this is actually separable because in this case, we have x as our input variable. So in this case, we can write f of x as 8 times x, and g of y can just be treated as a constant function. So in this case, this will be an example of a separable differential equation. Okay? But something like x to the 4th times y plus xy squared, that would not be an example of a separable diffEq because there's no way you can separate the x and y variables into their own functions. So this will not count. So with that reasoning in mind, let's take a look at the other two. So would this be an example of a separable differential equation given the definition we have? Who says yes? Who says no? Good. Is this example of a separable diffEq? Okay? And then for this last one here, so I would say let's do this. How about thumbs up if you say it is, and then thumbs down if you say it is not? Good. A lot of thumbs down. Great. So this is not a separable DPQ. Okay? The first two are, last two are not. And we'll do another quick example of this. So we'll show that dy dx equals x cubed times e times y minus x to the fourth is separable. So here's what we'll do. So how would we want to break this up so that we can show that this has the form f of x times g of y? How would you want to break this up? So we have x cubed here, which is fine, but now we have x e to the y minus x to the fourth. So how should we break that up? Go ahead. Yeah, so it's x cubed and then times, what was it?
E to the y divided by e to the
X to the fourth. Yeah. So yeah, you could do that. You could say, e to the y divided by e to the x to the fourth. But for our purposes here, because we have a product, we'll just go ahead and rewrite this as e to the negative x to the fourth. Okay? So then what you realize is that, all right, that means we have dy over dx equals x cubed times e to the negative x to the fourth times e to the y. Okay? So then this part would be f of x, and then this would be g of y. Okay? So that's just a quick example showing that this is a separable DPQ. Okay. Now, let's take a look at some new definitions. So a solution to a differential equation is a function that can be plugged into a DPQ and have it be true. Okay? Okay? So that's what a solution to a DPQ is. But a particular solution is just a solution with no arbitrary constants. What I mean is the usual C constant is our arbitrary constant. Okay? So a particular solution to dy dx equals 3y is y of x equals 2 times 3 to the x, as shown below. So what we'll do is we'll plug y of x into our differential equation and show, okay, if we plug this in, both sides should be equal to each other. So in this case, dy dx, so all we're doing is we're taking the derivative of y, this function here, with respect to x. So doing that should get you what? We're just applying chain rule on this, so we're just taking the derivative, not the antiderivative. Go ahead. Remember, derivative, not antiderivative. There you go. So it's 6 times e to the 3x. Okay? Which you notice is just 3 times 2 times e to the 3x, right? So that's just 3 times y. So that shows that 2 times e to the 3x is not only a solution, but because it has no arbitrary constants, it's a particular solution. So, right? So that's that part. So now let's take a look at example 1 to get a better idea of what's happening. So you guys have seen this type of problem in 16010 where, you can write this as, some constant times e to the kt. But we're actually going to show here why that is using what's known as separation of variables. So in this case, we have y of, if we let y equal y of x, so we let y equal y of x, this implies that by our assumptions here, we have y prime of x equals k times y of y of x for all x, right? So what you notice is that, oh wait a minute, I have y of 0 and y prime of 0. So how could I use this to figure out, I could actually use this to figure out what k is, right? So how would I do that here? So in this case, we let x equal 0, we have y prime of 0 equals k times y of 0. And the only reason I can do this is because I have the function at a particular value and its derivative at that same value of x. So, using our data here, how can we get, what would the value of k be? So what is the value of k given our data? Yeah, just 2, right? Because y prime is 12, and then times k equals k times y of 0, which is 6. So you should be able to see pretty quickly that k is 2 in this case. So we have y prime equals, or not just y prime, but I'll just denote this as dy dx equals 2 times y. Okay? So taking a look at this, we notice, okay, thumbs up, or if this is a differential or separable DFQ, thumbs down if it is not. Raise your hands high so I can see them. Okay, yeah, I'm seeing a lot of thumbs up, so that's indicating that's a separable DFQ. So what I'm going to do is I'm actually going to, in this case, divide y over to the other side. So divide y to other side. Okay? Whoops. There we go. So here's what we get out of this. If we do that, well, we have 1 over y dy dx equals 2, right? So what I'm going to do now is I'm going to sort of quote-unquote multiply by dx. Multiply by dx. So we have 1 over y dy equals 2 dx. Okay? Now this is a technique that's known as separation of variables. So this is separation of variables. So the idea is basically we have to put g of y and dy on one side and f of x and dx on other. Okay? That's the idea behind separation of variables. Okay? So now that we do that, we can then say, all right, now let's integrate both sides with respect to their specific variables. So we have 1 over y dy equals the integral of 2 dx. All right? So now we treat these as our own separate integrals and set them equal to each other, basically. Okay? So the integral of 1 over y with respect to y is equal to what? From the last quiz? Good. Make sure you remember that absolute value. Good. Because I did dock points if you forgot the absolute value. Okay? And then the integral of 2 with respect to x, well, in this case, you have 2x, and then here I'm actually going to incorporate the plus c constants. Because here, even though you could add plus arbitrary constants to both sides, it's not really necessary since you just have an arbitrary constant on both sides anyway, so you only really need to put it on one side. Okay? So now, let's go ahead and isolate y and see what happens. So, here we have, alright, we have natural log of absolute value of y. So, what can we say that's absolute value of y is equal to if we apply the right operation here. So what do we need to do to both sides to get absolute value of y by itself? Yeah?
Raise both sides to into the, or like e to the.
Yes. Yeah. So e to the 2x plus c, right?
Yeah.
Okay. So this gives us this, right? So here we can actually break this up a bit further as e to the 2x times e to the c, right? But remember, c is an arbitrary constant, right? So in this case, the c here can essentially absorb this whole thing in the sense that we just get another arbitrary constant, c times e to the 2x. So in this case, this is still arbitrary, so that means this is still an arbitrary constant here. Okay? So here, we get absolute value of y equals c times e to the 2x. So how do you think we could figure out what c is given what we have so far? So remember, we have y of 0 equals 6, right? So how do you think, so how could we get the value of c given that? So in this case, we say, all right, in this case, if x equals 0, that means y equals 6, right? Y equals 0, y equals 6, and x equals 0. So in this case, we have absolute value of 6, which is just 6, equals c times e to the, 2 times x, which is 0. So this is just equal to c, right? So ultimately, we have c is equal to 6 here, all right? So as a result, we have the absolute value of y of x is equal to 6 times e to the 2x. Okay? Now you might think, all right, well, that's great and all, but we're looking for y of x, not its absolute value. But here's the thing. So I'm just going to do this. So in this case, that means, okay, if absolute value of y is equal to this, that means that y of x is equal to either 6 times e to the 2x, or y of x equals negative 6 e to the 2x, right? So, but remember, wait a minute, we still have y of 0 equals positive 6, right? So based off of that, what can you infer about these two options here? So which one can we not have? Which one is not the one we should have? Negative, right? So because of the y equals 0 equals positive 6, second one's not an option. So that means your solution is actually going to be positive 6 times e to the 2x. Okay? So that's your solution to that. Any questions on that example? Okay. So one important thing I'll remark here, just because this is pretty important. So I know you saw this in 160.10, but I'll reiterate it here because of how important this is. So general solution to y prime equals k times y is y of x equals c times e to the kx, where c equals y of 0. Okay? Okay. So the thing is that even though we saw this in 160.10, most of you probably just saw, okay, here's the solution, and it holds because of reasons you'll see in this class. Well, now you use separation of variables to see why exactly that is. So that's your answer to that question. All right. So any questions on that part? Okay. Well, a bit. Okay. Now let's move on to the next example. So now we have solve the following differential equation below where y equals 2 if t equals 1. Okay? So in other words, if we let y equal y of t here, then this data here says that y of 1 equals 2. So just keep that in mind for later. Okay? So again, if we take a look at this, so does it look like we have a separable differential equation? So thumbs up or thumbs down? Okay, a lot of thumbs up. So again, good, separable DPQ. So in this case, we need to go ahead and break this up into, put everything with y and dy on one side and everything with t and dt on the other, so as per separation of variables. So in this case, if we want to have, we have something times dy and then equals something times dt on the other side. So if we break this up using separation of variables, so put everything with y on one side and everything with t on the other, what would you end up with in this case? What would you multiply by, so how would you want to get y over to the other side here? So, go ahead.
Wouldn't you end up with 3y dy equals natural log of t dt?
Yep, 3y dy equals natural log of t dt. Good. Alright, so here's what happens with this. So, if we do that, we'll go ahead and then integrate both sides. So here's what happens. So with this side here, you should be able to see pretty quickly that this left-hand side becomes 3/2 times y squared, right? But here's the kicker. Now we need to integrate natural log of t dt, right? But well, wait a minute. If we go back to that little remark we had at the very end of class, remember we had that like procedure for how to integrate functions. We had, if this was a less than r integral, do that first. Otherwise, try to do its substitution, and then last resort, apply by parts, right? So we definitely don't have an antiderivative for natural log of t, so your Calc 1 integral is not going to help you here. Let's try substitution. So what would there be a valid substitution here, if at all? So thumbs down if you think there is, thumbs down if you think there is not. Thumbs down. Well, yeah, so in this case it would be thumbs down, so there's no good substitution here. So in this case, you have to apply by parts. So only option is by parts for this guy right here. So in this case, we need to be careful here. So we have u, and we have to break this up into u and dv, right? So remember, in this case, if we remember our LIATE acronym here, what would be the appropriate choice for u in this case? Natural log of t, right? So you might think, okay, well, what would be the by parts thing here? Because we just have natural log of t and then times dt, right? But remember, by our acronym, we have to use natural log, and then dv is, remember, everything else, right? So dv is just dt here. So you should be able to see pretty quickly that du is just 1 over t dt, and v is just t, right? So if we do that, we have u times v, which is t times natural log of t, minus integral of v du. So t times 1 over t dt. So nice thing is these t's cancel each other out. So we're just left with t times natural log of t minus integral of dt, right? Or if you prefer, 1 times dt. Okay? So this ends up with a nice antiderivative of what? So t times natural log of t, and then what would follow suit from that? So then minus what?
Minus t.
plus,
Plus C, yeah.
good, remember, plus C. Okay? Okay, so now let's go ahead and put everything together here. So what this tells us is, okay, so we have 3 halves times y squared equals t times natural log of t minus t plus c. So now what we're going to do is now we're going to multiply 2/3 to the other side here. So we have y squared equals 2/3 times t times natural log of t, then minus 2/3 times t, and then plus, remember, again, c is an arbitrary constant here. So again, if you have 2/3 times c, it's just going to be another arbitrary constant, right? So in this case, you're just going to end up with c here. So c arbitrary. So quote-unquote absorbs 2/3. Okay? So now, here's where I'm going to take things in a couple different directions. But one of them is fairly short, so I'll start with the shorter one. Okay? So if I go from here, then what I can do is I can actually get that the general solution to the diffie-q is, so in this case what we need to do is we need to get y all by itself here, right? So in this case, all we need to do is take the square root of both sides, right? So we have y of t equals, so if we take the general solution here, then it seems like, all right, all we need to do is just take the square root of both sides, right? So we have 2/3 times t times natural log of t minus 2/3 t plus c, right? But wait a minute. Remember, what's the general rule for taking the square root of both sides? Yeah, we have to incorporate plus or minus here, right? So this says that the general solution to our differential equation is y of t equals plus or minus square root of all this, right? So that gives us the general solution, but remember, we have a particular piece of data here, so we need to incorporate that into our solution to get the particular solution, right? So let's go ahead and do that. So the only reason why I did this was just so you guys know how to respond to this type of problem when you get to it in the homework. So now let's go ahead and figure out the particular solution from this. So now what we're going to do is we're going to use our data here. So we have if y equals 2 and t equals 1, starting from here, let's see what c is. So y equals 2, that should get you 4, because 2 squared is 4. And equals 2/3 times 1 times natural log of 1, and then minus 2/3 times 1 plus c. Right? So now let's go ahead and simplify this. So if we clean up the right-hand side here, so we have 2/3 times 1, but then times natural log of 1, which is 0. Okay, so this term goes away. And then minus 2/3 times 1, so ultimately you're just going to have negative 2/3 plus c is equal to 4. So a quick bit of algebra later should then tell you that c is equal to what? So what number over 3? What's that? It's just 14, right? So that will give you the value of c here. So in this case, we say, all right, that gives us, so I'm going to do this. So we have y squared is equal to 2/3 times t times natural log of t minus 2/3 t plus 14 over 3. Okay? Now, as per the reasoning here, well, just take the square root of both sides, and then that gets you y of t by itself, right? So that gets you plus or minus the square root of 2/3 times t times natural log of t minus 2/3 t plus 14 over 3. Okay? But remember, as similar reasoning as to the last example, that means that we have either plus square root of all this or minus square root of all this, right? So now remember, if y of 1 equals 2, that means by similar reasoning as the last problem, that means we need to either have plus square root of all this or minus square root of all this. So using that reasoning, which one should it be? What's that? The positive one, right. Because remember, y of 1 is equal to 2, which is greater than 0, right? So that means y of t should be positive square root of 2/3 times t times natural log of t minus 2/3 t plus 14 over 3. Okay? So this would be the particular solution in this case. Okay? So that's example 2. So any questions on that one? Okay. So I'll give you guys a second to catch back up on that, and we'll go on to example 3 then. What's that?
Wait, where did the 4 come from again?
Yeah, so in this case, if we let y equal 2, then this becomes 4. Any other questions? Okay. Alright, so moving on to example 3. So we have to write a diff dq describing each of the following types of proportionality. So the first example is we have a strain of bacteria that grows at a rate directly proportional to its population at time t. Now, sometimes they use the word directly, sometimes they just say proportional. So if they just say proportional, assume it's directly proportional. So in this case, we have dp over dt. Now, if this is going to be equal to just a proportionality constant k, and then times p. So what's happening here is that, remember, dp dt is, remember, the change in population. Remember, this thing proportional means we have to incorporate some constant k, which we'll denote as k, and then times proportional to whatever we have. So in this case, it's the population p at time t. So we just have to multiply by p here, and then that's it. Now, one thing to note here is that the problem states that the problem grows, the strain of bacteria grows at the rate of k, or at the rate of the proportionality here. So population grows. So remember, that implies, if you recall from 16010, that just says that this means that k has to be greater than 0. That's all that means. Okay? So that's that example. Now, the next one is similar. So we still have a strain of bacteria grows at a rate inversely, but now it's inversely proportional. So in this case, we still have dp dt, and we still have k, but now inversely proportional means that we now have to take p here, and then instead of multiplying it by k, we now have k divided by p. Okay? So that's that example. And then the last one is jointly proportional. So in this case, I stole this from the first time I took this class, and I know this is aged very poorly, but I kind of just took it because I didn't really think about this too much, but the rate at which 8,300 people become infected is jointly proportional to the number of people already infected, p, and the people not infected. So in this case, dp dt equals k, still our proportionality constant. So now what we have to do is we have to multiply k by the number of people already infected, so which is denoted by p. So infected. And then multiply that by the number of people not infected. So if you have a group of 8,300 people and p people are already infected, then what's the number of people not infected? 8,300 minus p. Good. And then this is not infected. So that's example 3 in general. So any questions on any of that? So this is just there to say, you know, if you end up encountering these types of proportionality on this homework or future homeworks, you now know how to respond to them. You now know what they should look like. Okay. Okay. So moving on, let's look at example 4 then. So example 4 states that we have a radioactive element with a half-life of 5 years. If the element initially weighs 4, it should say grams. I think I had initially a typo that said pounds, but this should be grams. Find the amount left after 12 years. Okay. So I'll just recall this definition from 16010. Definition, so half-life is amount of time it takes to lose half its original mass. Okay. Oops. So half-life is the amount of time it takes for a sample to lose the half of its original mass. Okay. So in this case, in these types of problems, assume P of t equals c times e to the kt for these types of problems. Okay. So in this case, further, we're also given, let's see. So P of t equals this, and the element initially weighs 4 grams. That means P of what equals 4? What's that? 0, right? So P of 0 equals 4. And then we also have the half-life is 5 years. So that means P of 5 is then what? 2. Okay? So given this, we have to find the amount left after 12 years. So in this case, we have to find P of 12. All right? So if you recall from our remark at the end of example 1, C corresponds to the initial amount, right? So we already have what C is. So P of 0 equals C equals 4. So P of t equals 4 times e to the kt. So now all it remains to do is to figure out, well, what is k? So here, we'll just go ahead and let t equal 5 to figure that out. So P of 5, that on the one hand equals 2 by assumption, but then plugging that into here, we end up with 4 times e to the 5k. All right. So now, let's go ahead and solve for k in this case. So what we have here is that, all right, if we divide both sides by 4, we should have e to the 5k equals 1/2. So, going through all that, and then if we end up solving for k, what is the exact value of k here? Go ahead. Yep, it's natural log 1/2 over 5. Okay, good. So that's just a quick bit of algebra. Take natural log of both sides, and then divide by 5, and there you go. So from there, we should be able to get at the end of the day that P of t is then 4 times e to the natural log of 1/2 times t over 5. Okay? So that's our P of t particular solution now. So now we just got to find P of 12. So let t equal 12 to get 4 times e to the natural log of 1/2 times t is 12 over 5. So plug that into a calculator, and at the end of the day, you should end up with, if we round to 4 decimal places, we have 0.7578. And in this case, this is in grams, so that's our final answer. Okay? So, any questions on example 4? Alright, so the last example I want to get to then is example 5. So here's what we have with example 5. So after 10 minutes in Joe's room, his tea has cooled from 100 degrees to 50 degrees Celsius. If the room temperature is 20 degrees, we need to find the temperature 50 minutes later, rounding to the nearest hundredth. Okay? So with this type of problem, it doesn't really say this, but you do need this. You need what's known as Newton's cooling formula. Okay? And here's what it states. So you have d big T over d little t. So if we denote big T of little t as temperature of T at time t, okay, then this is equal to some constant K times T minus S, where S equals surrounding temperature. Okay. Now, thankfully, the problem actually gives us S pretty quickly as the room, or in this case, surrounding temperature. So in this case, we just have 20 degrees as our surrounding temperature. Okay, so here's what we have with this. So one thing to note here is that if the temperature starts, so we're going from 100 degrees to 50 degrees Celsius. So we actually are given two values of the temperature at two given times. So if we start at t equals 0, assuming that we're starting with 100 degrees, then that means after 10 minutes, with t in minutes, that should give you that t of 10 is 50. Okay? So that means that we're given this, and then we need to find t at what time, if t is in minutes. Yeah, t of 60, right? Because we need the temperature 50 minutes later. So 50 minutes past the 10 minutes that have already happened. So we need to find t of 60. Okay? Now, one thing to note here is that we do have that it's k times t minus 20, which is, okay, already, fair enough. But one thing to note here is that, so notes, t minus 20, I claim that's actually greater than 0. Yep? Oh, sorry. So one thing to note here is that I claim that t minus 20 is greater than 0. So if we're starting at 100, so if we're starting above the room temperature, then I claim that t minus 20 is going to be greater than 0. Any thoughts on it as to why? Yeah, because the room temperature is 20 degrees, right? So T hotter than room temp, and it can't get colder. Okay? So the room temperature is 20 degrees Celsius, and it can't get colder, and the T can't get colder than that, so that means that t minus 20 is always greater than 0. Okay? Okay, so now that we have that, we have dt over d little t is our diffie q. And you should be able to see pretty quickly this is a separable diffie q. So, in this case we have, if we go ahead and use separation of variables, you should be able to see that we have d big T over, so dt over t minus 20 is equal to k dt. So you should be able to see that pretty quickly in applying separation by variables. So if we do that, then let's go ahead and then integrate both sides. Okay. So So now if we integrate both sides, well, the right-hand side you should be able to see pretty quickly is just kt plus c. But then what about the left-hand side? What is the left-hand side going to be? Go ahead.
Natural log of the absolute value of t minus 20.
Yep, natural log of absolute value of t minus 20, right? But remember, as we already said, t minus 20 is already greater than 0, right? So in this case, we can actually do one better and say this is actually just natural log of t minus 20 equals kt plus c. So by this remark here, we can get rid of the absolute value because we don't need it here. Okay. So then now we can then go ahead and we can go ahead and take everything, put the raise both sides to exponential to get t minus 20 equals e to the kt plus c. And then again, c is an arbitrary constant, so this is just c times e to the kt. So, at the end of the day, we have big T of little t is 20 plus c e to the kt. Okay, so from here, let's go ahead and start solving for our constants here. So, if this is the general solution here, let's go ahead and start by first finding c since we have initial data here. That is, we have t of 0 equals 100. So if we plug in t of 0 equals 100 into our solution here, then we have, let's see, t of 0 equals 100 equals, let t equal 0 here, to get 20 plus, in this case, c times e to the 0, or just c. So you should be able to see pretty quickly from this that c is just 80. So big T of little t is then equal to 20 plus 80 times e to the kt. So now the last thing we need to do is figure out what k is. So now here's where our t of 10 equals 50 assumption comes into play. So t of 10 equals 50. So for that little t equal 10 here, we then have 50 equals 20 plus 80 times e to the 10k. Okay? Oops. So, if we then go ahead and solve for k here, well, let's see what we get. So, first off, if we first solve for e to the 10k here, we should get what nice fraction out of this? Go ahead. Yeah, just 3 over 8, right? Okay. Now, by similar reasoning as to what we saw in the last example, you should then be able to get that k, if you solve for the exact value of k, that's just the natural log of 3 over 8 divided by 10. Okay? Okay, so now we have the exact value of k here. So now, that means the particular solution we have is big T of little t equals 20 plus 80 times e to the natural log of 3/8 times t over 10. This will be our particular solution we get here. Okay. And so the last thing we need to do is say, all right, we ultimately got to figure out, well, what is t of 60, right? So all we do is just let little t equal 60 here. So we get t of 60 is approximately, so the problem states we need to round to the nearest hundredth as per its last sentence. So doing that will get you 20.22, and that's the temperature in degrees Celsius. Okay. And that's example 5. Any questions on any of that? Okay, well, so just a heads up, this is my last lecture as your substitute instructor, so Pavel will be back starting next Monday. And then, yeah. And also, if you have not picked up your quiz for last time, please do so before you leave, otherwise you will not be able to pick it up until after the exam. So, yeah?
There's no lecture on Monday, right?
Correct, no lecture on Monday. Otherwise, I'll see you guys around and just have a good rest of the semester.